Okay, so this is a production by Chris and myself, and I have to say that Chris has come up with many of the ideas which has made this work. I'm not at the moment located in Maynooth. I'm located in Newcastle, so there's been urgent email and urgent R files across the Irish Sea. So over the years, we've been sort of talking about, can we take the correlation coefficient to bits? And it was about 3 years ago, Chris said, well, actually, it's really quite easy, and I'll show you what to do. So the structure of the talk, it shouldn't be too complicated. So I'll just sort of introduce where we're coming from. I will take a draft of my cup of tea every so often. I'll talk about the Pearson product moment correlation coefficient and then how we compose it. And then it dawned on it after we'd had a go at mapping some of these that we actually needed some confidence intervals for the coefficient. So I'll talk about then. And then I've talked about 3 experiments. So one uses the well-known Georgia data set, which is in GW model. And then we just sort of wondered, it's one of those things you do over a pint of Guinness in the pub, are correlation decomposition and the global correlation and the autocorrelation decomposition related? And then, what morph effects are there? And does that point to the right scale, where right is in square coats, to do the analysis? And we'll finish with some conclusions. And I've got about 7 minutes left. Okay then, so lots of us teach, introductory statistics classes, and we all cover the Pearson product moment correlation coefficient. And these are widely used whole map statistic. I tried to go back to the origins of it to see if Pearson actually wrote a paper, but it turns out that it might have been Galton who thought it up, and he credits some. So the origins are in the midst of time. So what does it do? It gives an indication, and sorry about the typing errors here, of the strength and the direction of the association between 2 variables. Now we just get one number out, sort of 0.6, and nobody really knows what that means. And there have been previous conferences where people have tried visualizing correlation and visualizing whether one can tell the difference between 0.6 and 0.7. But it struck us that this might mask something underneath, and within that the coefficient, there is element of heterogeneity. So this then leads us on to a number of questions. So can we decompose the correlation coefficient to explore where there is spatial variation, and presupposing that our data are for some sort of spatial unit on the surface of the Earth? Then is there a relationship between the global correlation and the autocorrelation of the decomposed components? And then the third one which came to mind is there a morph effect? What does it have? In a sense, we really had not much of an idea what was going to come up, so it's been quite an interesting journey. So then, if the variation of the decomposed elements, and we'll look at that in a moment, is not uniform, what are the implications? Well, we're looking at the relationship between 2 attributes, so it may be more related to the other one in some regions, but not in others. So hence, we need to think about the nature of the confidence intervals. And if we're just going to use the whole map statistic, the sample correlation coefficient, then that effectively masks some of the detail which might shed light on the geographical processes which are at work. And then there's other things which might happen. So if we observe heterogeneity, there's a third variable which might act as a catalyst to cause the variables locally to become more connected. So what we're going to do in the paper then is to undertake a decompositional approach to pairwise correlation. So what are the individual contributions of location, and which of them have the most influence on the overall correlation? correlation value. Well, I'm sure we've all typed this one in our lifetime. It was fun typing it in Markdown. So the correlation coefficient, Pearsons, is the ratio of the covariance of two variables, and we'll call them x and y, and we'll assume they have a roughly normal distribution to the product of their standard deviation. So on the top there, xi minus x bar, so x bar is the mean of the x variable, so the x's are the deviates about the mean of x, and yi minus y bar are the deviates from the mean of y. The top gives us the measure of the covariance, and the bottom gives us the measure of the standard deviations, and we take the product of those. There probably should be some n's in there as well, but this is the global one, so they cancel each other out. So, okay, so yeah. And it's a simple R function. You give it two variables, but hides underneath this, and what can that actually tell us? Now you can look at other ways of rewriting the sample coefficient. We'll call it RP. It's the covariance to the product of the standard the ratio of the product of the standard deviations, and we've used up one degree of freedom in here. So we've got n multiplied by divided by n minus 1. Now, if we arrange that slightly, that gives us 1 over n minus 1, which tends to 1 as n is large, multiplied by xi minus x bar, y minus y bar over sx and sy. So that gives us effectively then it gives us these the z-scores of the x variable and the y variable. It took me some time to realize that this could be done, but if you multiply those to do as and take the vector sum, then you get the correlation coefficient. And this is the key to it all. So taking that apart, the covariance is the upper part, and the sample the standard deviations are in the lower part. And another way of looking at i's, not only does it index each observation, it also indexes location in a spatial data set. So that means if we've got a boundaries which this refers, then we can start and map those. So the form of RP on the right, so going back to there, is effectively the product of the sum of the products of the z-scores for the xi and yi variables over those locations I is 1 to n. And so what we're looking at here is that each individual term, so each individual z-score product, is the contribution of area I to the overall sample correlation value. When you add them up, you get the sample correlation value. So rather interesting, we can actually treat correlation as a liter, and the individual z-score products, we'll call those the correlation components, and I think that letter is xi. Okay then, so where does this take us? What does it mean? Okay, it gets a bit complicated here because we're actually dealing with variation in two variables. So it depends on the sign of the product. So if both deviates are positive, the product is positive. If both deviates are negative, the product is positive. And if one deviate is positive and the other negative, then the product is negative. And we can calculate these for each location, and we can then map those particular values. And it starts to give some indication of what the spatial pattern might well be. Now, some of those deviates, the xi's and yi's, where they're near zero, they're going to result in a product which is near zero. So that's not going to contribute greatly to the overall value of correlation curve of the global correlation coefficient. Whereas if those are large, and large in a bivariate sense, then they are going to influence the direction and magnitude of the correlation. So we've now got to think about, well, you know, and I've always thought about confidence intervals as, you know, we go on about significance testing, but really it's all about, is it big enough to worry about, and are these z-scores big enough to worry about when they're mapped together. Now, I'll not put a map up quite yet because we'll just have a look through the examples. I'm just keeping an eye on the time here. So if the global R is the benchmark then for computing the two normally distributed random numbers. So what we do is we calculate streams of random numbers given a correlation of rho between them. So when rho is naught, the positive density function is known explicitly, and what I had to do was actually go through to the next door office where Chris is sitting, for those of you who's been to Maynooth, and say, can you come up with the magic for this? And he did it for rho equals 0, and then sort of pointed out actually it's rather complex when rho is not 0. So what we've then got to do are to use some numerical integration techniques. So we've done all of this in R, and it's got some very neat little things for calculating what we need. So rather than deriving the result analytically, and that doesn't then require me to ask the statistics office like in the next door office. So to generate the 95% quantiles, then we need to generate the pairs of random numbers. I'll talk about n in a moment, with a mean of 0, a standard deviation of 1, and a correlation of rho. So they correspond to random z-scores. And then we compute the product of each pair of those to obtain a vector of n elements. And then what you do is you identify the 0.025 and 0.975 quantiles of the vector, and that gives you your 95% percentage points. Okay, so how big does n need to be? So the more simulations we have, then the more sure we can be that the calculations of those critical values are in fact reasonably reliable. We did some experiments, and n does need to be reasonably large. So with our data around 10 to the 7, so 10 million simulations as a minimum, that only takes a few seconds on a standard laptop. And as far as I can remember, it's pretty well all vectorized in R. And what I mean by a standard laptop is the sort that you can go to Currys to go and buy. It's nothing, you know, nothing special, a domestic laptop. So to generate the correlated random numbers, given the two vectors of the independent normal variates, we'll call them x and y, with a mean of 0, standard deviation of 1, we can generate the random normal variables. So x dash is x, and y is related through x and rho through the equation rho x plus rho minus rho squared y. And that then means that x dash and y dash have a correlation of rho, and locations with xi values which are in excess of the critical value can then be mapped as being interesting. Now, the confidence interval actually depends on rho I. It's non-linear, and that's the reason that we use simulation to identify the confidence interval for our observed rho. Okay, so I've got about 5 minutes left, I think. So a well-known spatial data set is that for the 159 counties of the state of Georgia. There are a number of variables in there related to the proportion of residents educated at bachelor's level or higher, and the proportion of residents born outside the USA. And the data are available in a number of locations, including in the GW model R package, which has got the data and boundaries. So the global variation between the two variables, foreign born and bachelor's education, are about 0.67. Both variables have a positive skew. I'll pop a diagram of that up in a moment. There are 80 counties for the bachelor's education, the education attainment, 18 for the foreign born at the positive end. So there are some influential locations. And a bag plot would suggest that 8 of the counties are bivariate outliers. So on the left, we've got box plots for the educational attainment of foreign-born variables, and you can see there is actually a bunch of outliers at the right-hand end, and on the right-hand side, we've got the bag plot, which is a sort of two-dimensional bag plot. And the red zones are the ones which are the bivariate outliers. So interesting question is, where are they? So if we map the decomposition, well, it's not easy to see what's going on. It's not easy to interpret those results. Blue is high negative and red is high positive. And the critical values for that are 0.554 and 4.053 because they're the products of the Z-scores. Now we can show those on a scatter plot. So here are the variables, foreign-born and bachelor education. These are the ones which are the outliers in the bag plot, and they're pulling the correlation coefficient up. And ones in this zone are significant, ones in the middle are not significant in that sense. And the two lines delineate the shades of the plot, and we've used the same colors for the plot. So notice the right skew on the two distributions. And like I say, there are several counties where the large positive values create large Z-scores, and they pull the correlation coefficient upwards. So what we can do then is filter the plot to show only those counties where the values of xi, of xi rather, are beyond the 95% limit. Sorry, my typesetting has gone wrong. The colouring needs care. So counties which are plus, so high positive on both x and y are coloured dark orange. The counties which contribute negative are shaded blue, and the colours contribute towards the colours, the quadrant colours on the previous page. And then when we have a look, we discover the northwest orange groups. This up here contains the universities, it's mainly Atlanta, so it's got Emory, Georgia Institute of Technology, and Georgia State University. Down here is Athens, where we find the University of Georgia, and down here is a county which has got a low medium income and a descending population. This might suggest the effect of a third confounding variable. So, and it also works for Spearman's Rho and Kendall's tau. Now, what about then the correlation of the global correlation and the autocorrelation of the components? And is there a relationship between the two? So the initial thoughts would suggest that there might be. So we have a standard list of 40 variables that we use for mapping and analysis in Ireland. They're based on those used for the UK's ONS classification. You can find the data definitions at Chris's RPubs page. And therefore 3,409 electoral divisions in Ireland from the 2016 census. There are some variables that we can't match and some variables which are unique to Ireland. So I don't think the English census has the proportion of households with septic tanks. So there are 780 possible combinations of the variables. We can calculate the global correlation for each. So that's what's along the bottom. And we can calculate a global more and I for the correlation components and plot those on a scatter plot. I've added a lowest fit, and you think, ooh, that looks really quite interesting. So as the global correlation approaches zero, the autocorrelation also gets zero. And as it increases in both directions, then so does the autocorrelation. But, you know, that's a rather general statement, and there are some high global correlations where the autocorrelation of the components is low. That then led us on to, and I'm coming to the end here, some more issues. So that's the 3,409 spatial electoral divisions. We've got a set of nested units in Ireland, so we can explore the same relationships and look at the same patterns for counties, intermediate areas, electoral divisions, and the small areas. That's the official title of them. And when you actually have a look at it, it's not so obvious what's happening. There does seem to be interaction as the correlation approaches 0, then the autocorrelation, the more I autocorrelation does decrease. But for counties, it's very interesting. We get a greater autocorrelation range, and the autocorrelation also approaches goes negative. The small areas have the smallest range, and this then I've done is I've used the same scale on both X and Y here for comparison. So, you know, is there a right scale at which to undertake analysis? And, you know, Stan Openshaw was thinking about that 40 odd years ago when I was an undergraduate. Okay, so I'm run out of time. So this is very much work in progress. The decomposed components act as a leader. The sign and magnitude indicate the local strength of the covariance. We can identify areas of unusual values, which leads to questions of where and why. We can look at other relationships between scale and autocorrelation, and the computations actually turn out to be relatively easy. The only thing that's left is that we're Chris gratefully acknowledged support under Science Foundation Ireland's Investigator Award Programme, which is Award 15 IA 3090 called Building City Dashboards. Okay, and that's it from me. So I'll thank you for listening there.
Thank you, Chris. I think this was really great, Martin. So we now still have a few minutes for questions. Are there any questions from the audience? I'm looking at the chat. If you have a question, please put it in the chat. I will ask Martin to answer a few applauses. While people think, I will start with a very simple, easy question. Since you were talking about doing all the work in R and the slides being done in R Markdown, I was wondering whether you might have these available anywhere so that people can have a look. Hopefully very well commented, so that we can also understand all the math behind it.
Yeah, I do have some codes. So what I will do is I'll put the code together and I'll comment it all out. And if people want a copy of the code, so perhaps a function where you give it the two variables, you get the correlation coefficients and the indications of the ones which are significant, is probably all that's needed. And then a bunch of others. Actually, Chris has just said I could share the R Markdown, except that I haven't got any code for calculating the coefficient in the Markdown code. But I'll play around with the R stuff. Oh, Chris has just said he thinks he has.
All nice Markdown where you can just click a button and you can reproduce everything from scratch.
Absolutely, absolutely.
I don't see other questions coming up, so I will take chair privilege. Oh, maybe we do have a question. Could there be a link between this decomposition and some kind of multiscalar decomposition of the spatial signal Fourier wavelet, which allowed them to express correlation as a function of correlation at a different scale? So I read that. I have no idea what that means. If that makes sense to you, please answer.
It does, because I don't know much about Fourier decomposition, I'll admit, but it's an interesting question, and actually, the different spatial scales might well come out of a Fourier decomposition of the correlation coefficient. So perhaps when all of this, this pandemic stuff is at an end, and I'm able to get back to my office, then some of this work could actually go forward a little bit. But it's a very interesting session, just like to do just. Chris has just said possibly via an eigenvalue decomposition of connectivity. Wavelets are harder.
I think there is another question. The Kendalltown version of this would be very interesting since it's based on the relative ranking of all pairs and observation. I think Ray's look at the some spatial correlation. Have you looked at how the I versus local R compares to the spatial person?
Okay, just thank Levi for that question. Again, I have actually got the code for doing all three of these. If I can find it. And what I was trying actually to do was to have a look at some of the, the papers, because I can't find. It's such an obvious thing to do, but I can't find anybody who's done it. And I see that Dave Unwin has just asked to have a look into the leverage maps, which we'll have a look at as well.
Sounds good. I think I've seen couple of months ago a paper on local measure of correlations, which I think it might have some sort of like a local version of Pearson R, which might also have a link to what you are doing.
I mean, in the GW model, we've got the geographically weighted Pearson R, but that's different from what we're doing here.